So what we'll look at is using something called DistilBERT for classifying intents. And we'll use the fastai library and the transformers library to train and do inference on our DistilBERT model. So if you've heard of BERT, it's a transformer-based architecture, very popular. A lot of people doing interesting things with it. It's very good at classification tasks. And DistilBERT is a variation of that. It's a smaller version of BERT. So the model size is smaller, and also since it's doing less computations, you can make predictions faster as well. And we'll try that with our data set. So I won't go too much detail into the transformer architecture because that could be a workshop in itself. But we'll look at how to train that using these libraries on our simple data set. Okay, so this part is actually not that different here. I just copied the previous class and just put it here so we can look at it again. And here you'll see what we'll do differently here is right now, because our model is so much better. And also one thing I was going to add, forgot to add was, so this DistilBERT has been trained on a lot of data. So it's been pre-trained on something like Wikipedia dataset, so that it knows a lot more about language from beforehand. And how it knows that is through this process of transfer learning. And maybe you're already familiar with transfer learning, but basically the idea is you have some source task and you want to transfer the knowledge you learned from that source task onto another different task because they're very close to each other. And in our case, we'll use, DistilBERT uses something called language modeling to get to that process. So first, DistilBERT has been trained on a language modeling task, and what that means is given a particular sequence of words, it tries to predict the next word. So I crossed the street and then so it says, okay, well, tell me what the next word is. There are some more specifics to training DistilBERT that I won't get into, but that's the idea. And why do we do this language modeling pre-training task? We do it because it's by itself, it's a very difficult task even for humans. You know, if I told you, give you a sentence and told you complete it, what's a chance that you might be able to get it correct what I was thinking? That's why it's a good task. And when you force a model to learn this, it's forced to learn a lot about syntax, semantics, and code-like things about the world, like what comes after the word hot or cold. It was a cold food. Distinguish between words that are words that have in the same sentence mean different things based on context. So, for example, it's raining cats and dogs versus there are cats and dogs are very meaningfully they're very different, even though it's the same kind of words that are being used, right? And if you give it, and the other thing is if you give it enough data, so something as large as Wikipedia corpus and a huge model and enough computation, it can do a very good job of predicting the next word. And there's some research that it works better than auto encoding. I won't get into detail what auto encoding does, but briefly, instead of predicting the next word, it's reading in a particular set of words and then trying to predict them again with two different networks, two different models. Okay. And that brings us back to DistilBERT. So DistilBERT is a model that's been trained in this process. So once we did this language modeling pre-training bit, we said like, okay, like now let's try to make classifications based on this. So before we were trying to, in the pre-training step, we were trying to predict the next word given a sequence of words. But now we'll say, hey, given a sequence of words, give me what the intent of this particular sentence is. So okay, and which brings me to this, why we define this data set here again. Previously, we had these other steps, right? We, lowercased the words, we removed the punctuation from our training data to make it very simple. But now, actually, we don't need to, because the DistilBERT model has seen so much of the English language that it knows what punctuations mean. So now we don't need to remove them from our training set. We can keep them as they are. We'll load it again. So those steps are the same from before. And number object, and look at the data set. Okay. All right. So that looks good. I added a different data set that also you might want to look at if you want to practice with this notebook or something. It's from it's a Kaggle data set, and it has nicely a lot of nice like intent data sets here. So it's really related to the hospitality industry. So it's for flights, where what flights are available, blah blah blah, and like scalable intents. So if you want to practice with this after the workshop, this is a good to look at, and it's reasonably sized as well. There's like I think around 4,000 data points and like 22 classes, which is pretty good size for the task we're doing today.
Here's someone asked.
Yes.
Sorry, I just muted myself. Someone asked if this structure is important to have. So an intent column, a phrase column, an answer column.
This structure isn't important in like not in general, but if you're using like the classes that we've given in the notebook, they're expecting them to be in that order. So if you change, it'll still work if you change the order, but if you just change the names and columns, you'll have to make some edits to the code to get it to work. Does that answer the question?
Yeah, thanks.
Okay, I'm not getting any feedback, so I think maybe that's good. Okay, yeah, so if you'd like to, you can check out this other data set and play around with it. For us, we'll look at the data set that I had prepared before. And we have a little bit of code to get the transformers library and the fastai library to work together. So the transformers use their own kind of tokenizing system. Before we used spaCy tokenizer to train the naive base model, but now the DistilBERT has its own particular tokenizer class, and they'll use that. So we're in a small class here, which is the base tokenizer, and this inherits the fastai base tokenizer. There's some standard details here. There's the actual object. We define a max sequence length. So after a certain number of words, we just strip the sequence. We don't take anything after that. And just the model type, so we know what it is. For our case, it'll be DistilBERT. So, and during the tokenizing, we add these couple of special tokens. The detail, so we append and prepend with them. And the reason we do that was because it was trained in that way. The details I would encourage you to look in the paper, but these special tokens just tell you when a sentence begins and ends, just to keep it very simple. Okay, so we have that, and we can initialize our tokenizer. And then we also need a vocabulary. So because this model was pre-trained, it already has a set of vocabulary, right? So if it was trained on the Wikipedia corpus, then all the unique words in the Wikipedia corpus are its vocabulary, and we need to use that as well when we are converting our words into tokens and converting them into IDs that the model can understand. So there's two functions here. One, it takes a set of tokens, so just the string, and then converts it into the IDs. So previously, remember when we said, when we were training the naive-based model, we tokenized everything and then converted it using a count vectorizer, right? Where we just arbitrarily assigned a word, a number to just convert it into a number. And it did that for all the unique words in our data set. So for here, since it's been pre-trained, we just use the same set of same set of word to ID mappings that the model was originally trained in. And convert our data set according to the same mapping from the original model. And then we have this bit textify, so that does the opposite. So given a set of numbers, convert them into their respective words. And it's basically a dictionary mapping. So go from A to B and then B to A like that. Okay, so now we have that. And we have these other special classes, variables here, and what that's doing is, so fastai has these processors built in that you use when you want to convert your data set into one that is trainable, and it uses something called the Tokenizer Processor, which is what we just wrote above here, but using this special DistilBERT tokenizer, and then the numericalizer, which is what we wrote here to convert tokens to their IDs and then IDs back to their tokens. So we do that, and now we're ready to, we have the setup we want, and now we're ready to convert it into our text into tensors, basically, because models, deep learning models only take tensors as inputs. And we'll use the fastai library for that as well. And it uses this nice little API called the data block API. And if you look at it, it's actually pretty self-explanatory. So you have a list of texts, and you take a data frame, a pandas data frame. Remember what we had written our data set into a pandas data frame. So it takes that as an input. Okay, it looks at the phrase column, and it uses these two processors, the Tokenizer processor and the numericalized processor, to change them into IDs, right? So, okay, we changed our list of strings into list of IDs. Then we want to have a validation set, right? Because you always want to see how your model is performing as you train it. Is the accuracy going down or up? What's going on? You want to have some way to evaluate it. So here, fastai provides a simple API set, split by rand%, and by default, that takes in the list of text that we currently had, splits it, it takes like random 10% out of it, and then puts it in our validation set. And so, okay, once we have that, now we need to label this data set from somewhere. And that we also say, okay, label from the data frame is the same data frame that you took in the first step. And the column is intent. So we pass that value in there, and now it has all the things it needs. And this data bunch is just puts all this together into an object. And this data bunch object has all the details that we just looked at. Oh, well, it's this data frame, it's this processor, this column. Okay, what's the validation set? And puts that in a like little object as well. And it also lets us say, okay, what's the batch size we want? So every time you call next on a data bunch or a data loader, give me back 64 things at a time. And that's because deep learning models are trained in batches. So we can take a look at what this actually does. So once we call that, we can look at the data bunch. And this is the train loader, data loader. And it's just we're calling next and iter on it to see what we get back. Okay, look at that. We started from a bunch of strings, and now we have nicely shaped tensors already in the GPU. And that's what's great about the fastai libraries. It lets you do stuff like that with like 4 or 5 lines of code. And you don't have to like go through all the details of how we got from strings to like this nice tensors that can fit perfectly into a model. Okay, so we have our data ready. So now let's look at the model, right? There's a small class here, and this class isn't actually doing anything. It's just like a nice wrapper. We take in a transformer object and just initialize it and put it in the object, and that's it. And since so every model needs to have a forward function. So we define the forward function, and that's also, it's just calling the forward function from this transformer and returning the first object that comes back. And we return the first one because this transformer object is coming from the transformers library that we imported here, right? And when you call forward on an object from that library, it actually returns a bunch of things. So not just the prediction or which is the output we want, but also other metadata, other output from the model, or which we just want to throw away. So we just take the first one because that's all we're interested in. Okay, so we have our wrapper ready, and now we have a couple more things here. Initialize DistilBERT. So there's many different kinds of DistilBERT. If you hover on it, you can see the source too. And this DistilBERT model is for classification, so exactly for the task you want. If you wanted a DistilBERT for a language modeling, which is like predicting the next word, that'd be another class. Although they're different classes, the weights are actually shared. So the class adds the ability so that you can move from language modeling, so predicting the next word, to like predicting the next class type of task. So that's what we initialize here. And the class needs a configuration. So this configuration file defines how many layers it has, how many classes our data set has, more specific details about the model. You know, where does the vocab come from, stuff like that. Where do you load it from, all of that details. And that's just how the library is designed so that you can load these pre-trained models easily. And this is the name. So there's a bunch of different models with the same base architecture. They're trained on different data sets, and we'll just use this version of the model. The details are in the documentation, so I won't be going over them. And here, since by default, the configuration assigns 2 labels, so just predict A or B, we have more classes, right? Our classes are the number of intents we defined in the very beginning. And we have that in our data bunch, data bunch around here, where we converted our data set into tensors. And this class, how many number of classes, fastai, when you called these functions, it did that for you. It calculated all of that and put it in a nice object in a variable so you can access it again. And that's really, so here we just, in the config, we change the num labels to our set of classes. And the number of classes is kept in this variable in the data bunch. So we're ready with that. We have our DistilBERT and we have our wrapper. Now we can initialize the model. It'll take a couple of seconds to download it. And it's ready. So PyTorch doesn't have its own, so we have our model, we have our data, and now we're ready to train it. PyTorch doesn't have its own training loop, but fastai does. So we'll just use fastai again to quickly train this. And fastai uses something called a learner object to take in the data, the model, the optimizer will use, and also lets you pass in metrics like accuracy, or there's other stuff defined in the library too if you want, like mean squared error or something, or any other kind of metrics. You can also define your own if you like, and pass them in here. But we'll use the default ones, and with that we have our learner. So then we have something interesting going on over here as the list layers. And so, okay, let's look at the model. And see what it looks like. If you print it out like this, it shows you all the different layers in the model. And it's not a huge model. There's like 8, 9 layers or something. But there's a few. And you can see, okay, the first layer is just embeddings. That's converting words. That's converting your sequence of word IDs that we saw here into some word embeddings. And then you have your transformer layers. And you have a bunch of transformer layers because the deeper your model, the more complexity it's able to understand. And you have here, you have 6 transformer blocks. And then finally, you have your classification layer. So it's taking the hidden state from the last transformer layer and then outputting 5 features. 5 features because we have 5 classes. So it's outputting the probability for each of those classes. And usually you just take the argmax, the highest probability, and return that as your prediction. So these are all the layers we have. But it's a pretty huge model. So what we do is we split them up into these different layers, and actually it's already split up. This is we're just defining the split layers into a list, and we'll see why in a second. So one thing here I want to explain is that if you have this big model and it's been trained on some kind of pre-training task like language modeling, and if you want to now switch that to classification for your data set, it'll forget all the things it learned during language modeling, right? Because now you're just giving it new data, new optimizer, and you're training it again. So it'll forget all the things that it had learned so far. And it'll start making, so all that pre-training knowledge that you spent so hard modeling is going to be lost. And that's going to, if you just let it train for free, like that, without any uh, intermediary step in between. So what we do is we say, okay, well, let's split it up, and let's train a layer at a time. So not all of these layers together, but one at a time, so that we don't lose all this knowledge that we had accumulated in the pre-training step. And that's a widely known phenomenon that happens if you just without any freezing, if you do without any of these intermediate steps, if you just train right away, it's called catastrophic forgetting, and the model forgets all this thing you've learned so far. So we do it a layer at a time. So first we say, okay, well, let's just train these two last layers, and we call learn.freeze2, freeze2 minus 2, and then it just unfreezes just these two layers, right? And then we're also going to, there's this nice learning rate finder that's built when you're training the model in fastai. So you want to pick a nice learning rate where you don't jump too quickly or go too slowly either, right? And what this learning rate finder does is it takes a batch, calculates the loss, and then takes another batch, changes the learning rate a bit, and calculates the loss again. And it does that for a bunch of different learning rates. And then it lets you plot this graph. So here, as you can see, okay, well, first I started out around here, learning rate was here. As you kept going, okay, well, it's going down. If you keep increasing the learning rate, it's going down, down, down. And then around here, it's like the lowest, and then all of a sudden it shoots back up again. So this is like way too, the learning rate is too high around here. So we don't want to be here. We want to be somewhere around here. So the loss keeps going down, right? Which is what we want. Also, you also don't want to pick too low. So if you're around here, then your model is going to learn very slowly, and you'll have to do like 10 times as many number of iterations throughout your data set to converge. And we also don't want to be too close to here, because then you might overshoot too. But it's always better to train your models at a higher learning rate for a longer period of time, so that you can generalize and not be very fine-tuned towards your particular data set. And there's been research that shows that that's what happens if you train at a too low of a learning rate on the same data sets. If you try it on like something the model hasn't seen, then it can't predict properly because it's overfitted to that particular data set. Cool. Okay, so we're here, and we've unfrozen only the last two layers, and now we can start training. We do 3 epochs, and that. Then we unfreeze 3 more layers, or up to -3, so up to the last 3 layers, and train some more. Okay, we do the last 5, do some more, up to the last 8. Okay, so we started off at 34, we're at 45 now. And finally, we unfreeze all the layers and train for like, say, okay. So with just 4 intents and like, I think 300 something data points. Oops. We ended up with 76% accuracy on our validation set. And the losses kept going down, so if you keep training a bit longer, it'll probably get better. Okay, so now we have a trained DistilBERT model that's been fine-tuned on our data set. And now we can check the predictions. And for that, you just call learn.predict. And okay, it's turned tensor number 3. That's hard to know what that tensor might be. Um, this is actually just the, so remember how we said that word IDs are converted, words are converted into IDs. Our labels are also converted into IDs. So what time is check-in is probably some kind of ID between 0 and however many classes we had. So we can check that. So the first is the class. The last one is the probabilities. So we can so this just has the list of classes, in the actual string form. So we can just look up the right index. From there, and okay, well, it said it was the index here, so let's not do that. Okay, let's check out. This time the prediction was wrong. But now we get to come back and fix it. Um, and actually, fastai provides a really nice interpretation tool for your classification to see how your model is performing on your validation set. Right? And it's literally called text classification interpretation class. So we can run that and look at our top losses. And what this is showing you is for this particular text, prediction was this. The actual was in our label data set, this prediction, and the loss was for that prediction, this was the loss, and probability was this. You can also take a look at the confusion matrix. Super small, but at least you can see, okay, for hotel as their early check-in, it predicted uh, when is check-in once in our validation set, and where is the front desk located 3 times. You can make this better. And the top losses show you the worst performing validation sets. So these are the worst performance instances. So probably you need to add more of these uh, text instances in your training data set so that your model can get better. And this is sort of a cycling process. So I think Max had mentioned in his talk that, okay, you need to design good conversations, you need to design good intents. And this tool sort of lets you see, well, okay, well, I'm failing at these, for these queries. Solution, okay, well, just add more of them to the training set or similar ones to the training set, and then train the model again, and then now you can make the right predictions. And this is an iterative process that you go on and go over again and again to keep getting better. And with that, I think I'll take a little break and take some questions and then take a little break. Susanna, are there any questions for me to address at this point?
There are a few questions, yes.
Yeah, yes.
Yes, I'm just trying to structure this.
All right.
Let's see. So someone asked if you could train your own embeddings with DistilBERT and then just use a by-LSTM for a classification problem.
So, okay, so if I understand correctly, use the embeddings from DistilBERT, but feed them into a LSTM and then train it again, right? Is that
I think so.
okay? Yeah, that's also something to try. It's yeah, I don't know if it will be any better or worse. It's definitely that's something interesting to experiment with and see how it performs. But I know, for example, maybe DistilBERT is too small, maybe. But I know people have tried like using just BERT embeddings and then using BERT embeddings for other tasks with a much smaller model. Um, so that's definitely something that might work. Yeah.
I think she indeed meant to use BERT for the embeddings, not DistilBERT. That was my bad. Yeah.